The expression sin of x divided by x has as its limit 1 as x goes to 0. This is an important result which is needed in order to be able to differentiate trigonometric functions and eventually to derive power series expansions for them, and also to integrate trigonometric functions. So a lot of calculus depends on this result. Hello everybody, I am Mika Seppälä. In the next few minutes I explain to you why the limit of sin of x divided by x is 1 as x goes to 0. I have been discussing this almost every year during the last 30 years or so, and I still find excitement in the beauty of this argument. I hope you can appreciate me. Our task now is to understand what the limit of the expression sin of x divided by x is as x approaches 0. In order to be able to deal with this expression, one has to resort to the definition of the sine function and to the way angles are being measured. So for the definition of the sine function, one usually draws this picture where an angle is placed so that its starting side is the positive real axis, its vertex is at the origin, and then its ending side, this red half line, intersects the unit circle at the point whose x-coordinate is cosine of x and y-coordinate is sine of x. This is how the function sine is defined, and we must now use this definition to compute the limit of sin of x divided by x as x approaches 0. Consider the expression sin of x divided by x. Substituting x equals 0 gives 0 divided by 0. This is not a number. One may try to approximate the limit of sin of x divided by x as x goes to 0 by evaluating the expression sin of x divided by x for small values of x. If one does that, then a computer or calculator gives for x 0.1, it gives a value 0.99833. For 0.001, a calculator gives the value 0.99999, and for the value x equals 0.00001, a calculator gives as the value of sin of x divided by x 1.0000. So this leads to the conjecture that the limit of sin of x as x goes to 0 might be 1. Also, this picture that a computer draws of the graph of this function, the one shown here on the right, the red curve, seems to indicate that this limit is actually 1. But we have seen in other examples that one cannot trust on such numeric computations. Maybe what we are seeing here is rounding error only. So this conjecture that the limit of sin of x divided by x as x goes to 0 is 1 has to be justified differently. We cannot use this picture, the graph of the function sin of x divided by x, nor the table that I just computed for you as a justification. We must understand this in a deeper way, and that's what we are going to do next. I start by reminding you what angles are and how they are being measured. An angle is formed when a half line emanating from a point turns around that point. This point is called the vertex of the angle, and if the angle is formed so that the half line turns counterclockwise, then the angle is positive, otherwise it is negative. Here we have an example of a positive angle. The starting side is the blue half line emanating from the vertex, and the ending side is the red half line emanating, of course, also from the vertex. To measure this angle, we draw a circle of radius 1 with center at the vertex of the angle. It is this dotted circle shown here. The size of the angle in radians is the length of the circular arc enclosed within the angle. It is the length of this arc on the circle of radius 1 shown here in this picture. This is the size of the angle in radians. Next, I remind you how the sine and the cosine functions are defined. I start by considering an angle of size t. So here we have a positive angle shown here in this picture, and I place this angle in the xy plane so that the vertex of the angle is at the origin and the starting side is a positive real axis. Then the ending side is the half line emanating from the origin. It is the red half line. The size of this angle is t. It means that the circular arc on the unit circle indicated here in this picture is of length t. So t is the length of the green arc on the unit circle with center at the origin. Unit circle has the radius 1. So that's how this angle is measured. And next, I consider the intersection point of the red half line and the unit circle. It is this point indicated by the blue dot. The x-coordinate of that point is defined to be cosine of t, and the y-coordinate of that point is sine of t. This is how cosine and sine functions are being defined. Then, when we have those defined, we define tangent of t as being sine of t divided by cosine of t, and cotangent of t being cosine of t divided by sine of t. And now we have our basic trigonometric functions defined. Next, we observe that every point on the unit circle lies, of course, at distance 1 from the origin. This is in particular true for the blue dot indicated here. And this means that sine squared of t plus cosine squared of t equals 1. So this basic trigonometric identity follows immediately from the definition. Now we have considered positive angles t. A negative angle is formed when the half line turns clockwise. So the negative angle of size minus t is now indicated here in this picture, and sine and cosine for minus t are the y and x coordinates of the blue dot below the x-axis. Now this blue dot below the x-axis is a reflection of the blue dot above the x-axis in the x-axis. This means that the y-coordinate of the blue dot becomes negative of what it used to be, and this means that sine of negative of t equals minus sine of t. So that's the y-coordinate of the blue dot above is negative of the y-coordinate of the blue dot below. Cosine of t is the x-coordinate, and for both blue dots shown here in this picture, the x-coordinates are the same. And this means that cosine of negative of t equals cosine of t. So these basic properties of sine and cosine follow immediately from the definition. Let us take a closer look at what these definitions really mean. Cosine and sine were defined as the x and y coordinates of the blue dot indicated here in this picture. The angle is measured in radians, so the size of the angle in the picture is the length of this green circular arc joining the blue dot to the x-axis. Now the angle is positive, so sine of t is the distance of the blue dot from the x-axis, that is the y-coordinate. So it is also the length of this dotted vertical line segment indicated here in the picture. The distance of the blue dot from the x-axis is sine of t. This green circular arc joins the blue dot to the x-axis as well, but it does not take the shortest route. This means that sine of t is less than or equal to t for all t greater than or equal to 0. In fact, here we have strict inequality if t is positive. If t is 0, we have equality, then sine of 0 equals 0. The inequality just obtained, which says that sine of t is at most t for t non-negative, is very useful. If we further restrict t to be between 0 and pi, then sine of t is non-negative as well, and we have that for t between 0 and pi, 0 is less than or equal to sine of t, which is less than or equal to t. Now, if t approaches 0, then sine of t is squeezed between 0 and t and must therefore also approach 0. And this means, by the squeeze theorem, that the right-hand side limit of sine of t as t approaches 0 is 0. So what about the left-hand side? We have that sine of negative of t is negative of sine of t. And this means that also the left-hand limit as t approaches 0 through negative numbers of sine of t is 0. And now these one-sided limits of sine of t as t approaches 0 from the left or from the right are the same, and this means that limit of sine of t as t approaches 0 is 0. What about cosine? We have that sine squared of t plus cosine squared of t equals 1. This means that cosine of t is plus or minus square root of 1 minus sine squared of t. And if we limit t to be between negative pi over 2 and pi over 2, then cosine is positive. And then it means that cosine of t is square root of 1 minus sine squared of t. We are interested in what happens to cosine as t approaches 0. And this means that limit of cosine of t as t approaches 0 is limit as t approaches 0 of the expression 1 minus sine squared of t. And this is the same as square root of 1 minus limit as t approaches 0 of sine of t, and that limit squared. Now, the limit of sine of t as t approaches 0 is 0. We have already established that. Therefore, the limit of cosine of t as t approaches 0 is 1. So we have that limit of sine of t as t approaches 0 is 0, and limit of cosine of t as t approaches 0 is 1. Using trigonometric formula, the addition formula for sine and cosine, we get from this information that limit of sine of t as t approaches any number t naught is sine at t naught, and the same applies for cosine. These are nice properties of the trigonometric functions, and we need them just in a moment. We still need one more inequality that also comes almost immediately from the definitions. To get to that inequality, consider a positive angle t as shown here in the picture, and consider the yellow sector of the unit disk. Its area is determined, of course, by the angle t. So if A is the area of this sector, then there's an equation which says that the ratio of A to the area of the full disk is the same as the ratio of the angle t to the full angle. And this means that A divided by pi is t divided by 2 pi. The pi in the denominator of A is the area of the unit disk. Unit disk has radius 1, therefore its area is pi times radius squared, that is pi times 1 squared, which is pi. The 2 pi in the denominator of t is the full angle. And from here it follows that A equals t divided by 2. So that is the area of the yellow sector of the disk. Next we consider the right angle triangle shown here in the picture. Its horizontal cassette has the length 1. Its vertical cassette has the length tangent of t by the definition of the tangent function. Therefore, the area of this right angle triangle is base times height divided by 2, that is 1 times tangent of t, and that divided by 2. So the area of the right angle triangle of the picture is tangent of t divided by 2. Now, the right angle triangle of the picture contains the yellow sector of the disk. This means that the area of the right angle triangle is larger than or equal to the area of the yellow sector. If t equals 0, then all the areas are 0 and we have equality. So this means that the area of the yellow sector t over 2 is at most tangent of t over 2. We may multiply by 2 and we observe that t is at most tangent of t for t between 0 and pi over 2. So t must be less than pi over 2. For t equals pi over 2, tangent of t is undefined. But for these values of t, we have t is at most tangent of t. In fact, we have equality only if t is 0, otherwise there is a strict inequality. Now we have everything we need for the proof of the result of this lecture. So we have seen that for t greater than or equal to 0, sine of t is less than or equal to t is less than or equal to tangent of t. Now, if t is 0, we have everywhere equality. If t is positive, we have everywhere strict inequality. Now, if t is positive, then sine of t is positive, and we may divide by sine of t. So we divide everything by sine of t, and we get that sine of t divided by sine of t, which is 1, is less than or equal to t divided by sine of t, and that is less than or equal to tangent of t divided by sine of t. But tangent of t divided by sine of t equals 1 divided by cosine of t. And this is valid if t is positive, and of course we must assume that t is not so large that sine or cosine would be 0. So we assume that t is positive and less than pi over 2. Now we are interested in the limit as t goes to 0. So this restriction that t is less than pi over 2 has no consequence. So we have 1 is at most t divided by sine of t, and this is at most 1 divided by cosine of t. But we know that 1 divided by cosine of t approaches 1 as t approaches 0, because cosine of 0 is 1. Therefore, we may simply compute this limit by direct substitution. So limit as t approaches 0 from the positive side. Now we have been talking about positive values of t, of 1 divided by cosine of t is 1. And this means then by the squeeze theorem that also limit of t divided by sine of t as t goes to 0 through positive numbers is 1. Alright, so now t goes to 0 through positive numbers. Next we observe that minus t divided by sine of minus t is the same as t divided by sine of t, because sine at minus t is minus sine at t. So this means that the quantity t divided by sine of t takes the same value at t and at negative of t. And since now the limit as t goes to 0 through positive numbers of t divided by sine of t is 1, also the limit as t goes to 0 through negative numbers of t divided by sine of t is 1. and this means that the limit of t divided by sine of t as t goes to 0 through positive or negative numbers is 1. So we have shown the result that limit as t goes to 0 of t divided by sine of t is 1. This is usually expressed then by saying that limit as x goes to 0 of sine of x divided by x is 1. Now limit as x goes to 0 of sine of x divided by x is a quantity we started with, and for which we computed the values and observed by numeric computations that this limit seems to be 1. Now we have shown that indeed it is 1. I like this type of arguments. We just took a careful look at the definition of the sine function, and we were able to deduce from the definition of sine and cosine that sine of t is always at most t for t non-negative. And that just came from the definition. We didn't need anything else except to understand what the definition really means. And also in the same way, directly from the definition came the fact that t is always at most tangent of t for t positive. So these were the two ingredients that were needed to prove that the limit of t divided by sine of t is 1 as t goes to 0, and this then also means that the limit of sine of x divided by x as x goes to 0 is 1. This is how the result is usually presented. This is important because it is needed when we want to differentiate the sine function and then also the cosine function, tangent and cotangent and so forth. And it is also needed to differentiate the inverse functions, inverse sine, inverse cosine and so forth. So a lot of calculus relies on this result only. And the argument, as you saw, is very beautiful. It requires only detailed understanding what the definition really means. No fancy tools were needed. This is what mathematics is about.